Yeah, so you've seen the title. I'm going to be talking about the outer automorphism of the symmetric group S6. So I guess, why is this interesting? Like, I guess the thing that makes it interesting is you take the symmetric group Sn, that's the set of permutations of endpoints. So, S3 is all the permutations of 3 points. Like, how many of them are there? There's 6. You've got 2 choices where this one goes, and then 1 choice for the last one. So this is a group of order 6, and in general, Sn is a group of order n factorial, which I hope is familiar to everyone already. Let me know if not, because I'm going to be assuming some group theory stuff. So you got your Sns, and then for any group G, you've got the automorphism group. So you've got group G, you've got then the automorphism group of G, and that is all isomorphisms on G to itself. And that's obviously a group because isomorphisms are invertible. So you've got inverses, you can compose isomorphisms. So this is defined for any group. For a finite group, the automorphism group is again finite. The way to see that is it's going to be a subgroup of the permutations of the elements of any group, of the finite group, and that's again the finite group. And so the thing with the symmetric groups is when you take the automorphism group of the symmetric groups of Sn, what you get is it's isomorphic to Sn, but only when n is not 6. When n is 6, it's bigger. And you end up with, I think it's just the you end up with a group twice as big. I think it's just C2 times S6. I think someone correct me if that's wrong. It's definitely this order, and possibly this is a semi-direct product rather than a direct product. I think it's direct product. And so you got all the sort of normal ones here, and then here you have this kind of one sort of extra one, the weird one, that then gets times with a whole load of normal ones. And that there, that's called the outer automorphism there, the non-trivial element of this bit. And basically my goal for this is construct this bit for S6. Like, why does this exist? What is it? What's going on? And yeah, that's the plan. And I'll also talk a bit about why for all the other ones it's just the normal ones, and I'll explain what's normal about those ones and where they come from as well.
There's also an exception with 2, right? But it's in the other direction.
There is an exception with 2. With S2, the automorphism group is Sn. Yes, for S2, there's this sort of, these are the inner ones normally. So normally for Sn not 2, these are all inner, but for S2, so for S2 you have automorphism S2 is still S2, but the non-trivial element of this is an outer automorphism. Basically, for stupid reasons, it's because S2 is abelian. So it's still, it's the same as all the other ones, but it is an outer automorphism. I can talk about again why that is, what's going on there. For S2, yes, there is something strange there. Okay, let's start with some nice finite groups and look at their automorphism groups just to get sort of familiar with what that's all about. We got a comment. Let me find chat. Possibly people don't know what inner automorphisms are. I'm going to talk about that if we don't, at least in the case of symmetric groups. That's just sort of a brief introduction. So if I've lost you already, don't panic. I'll talk about it all more. Yeah, that's right. It'll be an automorphism that comes from conjugation. That's right. So let's do some examples. Let's What have I got? Right, first example. Klein 4 group. So this is a group of order 4. You've got the identity element in there. You've got A, B, and C. These are all non-trivial elements. These have all got order 2. And so you might have seen it as 2C2s, direct product of 2C2s. So click group of order 2. And so we've got, A squared is equal to B squared is equal to C squared is equal to 1, like the identity element. So hopefully we'll know what group we're talking about here. So what is the automorphism group? Has anyone got any ideas, any guesses what that's going to be isomorphic to? You can sort of just intuit from this, from what you know about the group, what it ought to be. Any guesses? Feel free to talk or put it in the chat. Just guess. Guess.
S3.
S3, yay! There we go. Why?
Because A, B, and C can be muted.
Exactly, yeah. So these 3 elements here are basically, they all behave the same. So yeah, you can sort of swap them and end up permute them in any way, and that will give you an isomorphism of this group. That's kind of the hand wavy version. There's a nice linear algebra way of sort of proving it, slightly less hand wavy, which I think is quite nice. Let's just do that now. So I'll just I'll outline that. So the linear algebra proof is this group is a vector space over the finite field of 2 elements of dimension 2. So if you don't know what the finite field of 2 elements is, it's very simple. It's the field that has 0 and 1 in it. And then our group becomes length 2 vectors over this field. So the elements are the identity element sort of corresponds to 0, 0, like the origin. A corresponds to like 1, 0, for example. B with 0, 1, and C with 1, 1. And then obviously this is just the group operation. Then here is addition. And yeah, hopefully that's all clear or familiar. So then what's the automorphism group of a vector space? The automorphism group of vector space is, anyone know? Any guesses? If you've got a vector space, what groups have you got? I'll give you a random vector space. And there's a
something like GL.
Yes, exactly. So the automorphism group of a vector space is the general linear group GL. So that's GL of our vector space. And so now to figure out what this is, you just need to do some linear algebra to figure out what that is. And there's various ways of seeing. I guess we should say it suffices to show that this has size 6, because an automorphism of this group, it's got to fix the identity element, because any automorphism has to fix the identity element, and then all that's left is 6 possible permutations of the other elements. So if you can show that there are 6 elements in here, then you get everything, because it's finite. There's only 6 possible things. You've got 6 things, you must have all of them, and therefore it must be S3. So I had a nice sort of linear algebra reason why this is the case. So GL is this group is too transitive on the linearly independent vectors, and that's sort of a general linear algebra fact. Basically, you've got two vectors, you put them in the columns of a matrix, and that will give you a linear transformation taking a standard basis to your two whatever vectors you've got x and y. And if these are linearly independent, you end up with an invertible matrix, so it's in there. And so this is too transitive, which means any two distinct elements can get sent to any other two distinct elements because of this. And if you can send any two of these elements to any other two, then obviously you've got all the possible permutations. So anyway, that's just a nice linear algebra proof of this that I quite like. Anyway, regardless how you want to see it, we've got this automorphism group here, which is a nice first example. Let's do another example. Cyclic groups. So what do we think is going to be the automorphism group of Cn, cyclic group for their n? So Cn, you can think of it as integers modulo n. That is like 0, 1, n with the operation of addition. So any guesses on this one? What do we think this is going to be?
Is it S2?
S2? Why S2?
I don't have an intuition for this yet, but I'm thinking maybe up to the symmetry of which direction you're going around the cycle, there's an automorphism involved there.
Sure. Yeah. So that gives you an automorphism. It's the full automorphism group is bigger than just that though. But that's correct that there is that one. Let's draw S12.
Well, if it's C4, that's right. Very small set of cases. C4. That is correct.
C4 will be that will be. Let's write that one. That's right. So C4. That's all of them.
I think I think I see the problem. So I guess with a some prime. I don't know if we say C5. If we take C5 as our example, then there's a. Would it just be C5? Or sorry, S5? No.
S5.
I don't know. I'll let you talk.
Thinking out loud. Yeah. So it can't be S5 because every automorphism has to fix the identity element. So it's got to at least be a subgroup of S4 permuting these guys at most. You've got, like you said, the automorphism sending 1 to 4, sort of swapping it with its inverse. That's one that we've definitely got. Any others? So in the case of C5, which of these elements, well, I guess which of these ones, we know this one doesn't generate it, which of these 4 generate C5? We know one does.
All of them do.
All of them do. That's right. So they all do. So that means we can send this generator to just any other generator we like. It could go there, it could go there. These are all going to give automorphisms. And we can also just fix it, leave it there. So we got at least 4 automorphisms now. And it's not hard to see that's got to be all of them because a homomorphism from C5 to itself is determined by where it sends the generator. We've sent it to all possible places, so this has got to be all of them. And so we know it's a group of order 4. Which group of order 4 is it going to be? Well, if you send 1, let's look at sort of what's the order of this, the automorphism generated by this. So you're going to apply it once, and you send apply it once. You're going to send 1 1 to 2. You apply it again. What does the automorphism generated by sending 1 to 2 do to 2? Well, if you're sending 1 to 2, then the automorphism generated by this must be multiplication by 2. And so 2 will get sent to 4. So if you do this automorphism twice, 1 will get sent to 2 and then to 4. And then, similarly, double this one again. You get it to 8. 8 mod 5 is 3, goes there and there. And so it's sort of 4. You got an order 4 automorphism. You have to apply it 4 times before 1 gets back to where it starts. And so all that is to say, this must be isomorphic to C4. And I guess the only other option was C2 times C2, if you know your small finite groups, which I'm sure we all do, I have no doubt. What have we got in the chat? Yeah, just talking about what I just said. Yeah, you can send 1 to any non-zero element. Well, that's the case for C5. Let's look at the next one. Yeah, we got the answer in the chat there. Let's talk about that. So if we look at C6, it's a bit more sort of highlights the general case a bit better than C5. So C6, cyclic group on 6 elements. Here they are. What are the generators? We've had it mentioned in the chat. They are sort of in general, I guess, and for C6 in particular, it's all the things co-prime to 6. So if you've got something co-prime to 6, and then you keep applying the automorphism, sending 1 to that thing, you're not going to end up at 0. You're going to sort of stay here and eventually get back to 1. I think that's what I want to say. Am I showing the right thing here? What we want to show is that sending 1 to something co-prime to 6 is an automorphism. So I guess what could go wrong? You can send 1 anywhere you like. What could go wrong is you might fail to be surjective. So for example, if you send 1 to 3, that's the multiplication by 3 map, not necessarily an isomorphism. And indeed, if we look at where everything goes when you multiply by 3, 0 gets fixed. 2, that goes to 6, which is 0 mod 6. 3 goes to 9, which is 3 mod 6. 4 goes to... Oh, I'm showing my terrible arithmetic skills here. 12. Is that right? Yes, that must go there. Goes to 0. 12 mod 6 is 0. And then 5 is minus 1 mod 6. Multiplied by 3, you get minus 3 mod 6, which is 3. That goes there. And so you see that automorphism, well, it's not an automorphism, it's not surjective, because we're not getting anything going to 1, 2, 5, or 4. And basically the thing that went wrong here is that 3 shares a factor with 6. So if you send 1 somewhere that's not sharing a factor of 6, which is any of these 4, you get an automorphism. And these are like I guess the group theory way of seeing it is that these 4 things are all the generators of S6, of C6, whereas 3 and 0 are not generators. So you generate S6, C6, sorry, if and only if you're co-prime to 6, and there's where your automorphisms come from. So for C6, it is that group, which is this is just notation for the things mod 6 that are co-prime to 6. So this is a group of order 4. That is our 1, 2, 4, 5, and this is the group operations now multiplication. It's an autism. Yes. In general, then, same thing happens. The automorphism group of Cn is, let me do my z's better, is integers mod z, mod n, co-prime to n, and then you take multiplication as your operation. And as was mentioned, I saw already, the order of this thing in general is the or the totient function of n. So the order of that is, well, that's not equal, but the order of it is totient function of n, which is, this counts the number of things mod n, co-prime to n. That's the definition of it. There's a nice link to number theory, and then this links to other things as well, like my favorite one is Galois groups of cyclotomic fields have this. That is the Galois group as one of those, and that's related to the fact that you're generated by root of unity, which is related again to cyclic group of order n and so on. But we're not talking about that today, so I'll stop there. We've got in the 5 case, automorphism group of C5 is C4, which is not S55. What do you mean by that?
The original post said it was the symmetric group of the size of the order of the totient of n as opposed to the cyclic group.
Fair enough. Cool. Right, fine. Cool, that's all sorted then. Right, there we are. That's cyclic groups. We know automorphism group of all cyclic groups. Fantastic. What is next? Next, I've got these symmetric groups. So I guess the next obvious group you could try and ask about is dihedral groups, but turns out it's a bit messy. Like, it's not nice. It's got an answer, but it's not nice, and it would take me too long, and I'll get myself confused trying to do it. And I don't know the answer anyway, because I haven't looked into it, because I looked into it enough to decide it was too horrible. So we're not doing that as an example, because it's a bad example for getting a good sense of these things. So let's go on to symmetric groups then. So yeah, we'll talk about the difference between inner and outer automorphisms for symmetric groups. So as was, I think, mentioned earlier, you've got the symmetric group Sn. If you take any permutation in here, what should we call it? Call it G. So that G is a permutation of n points, or call the elements of this thing 1, 2. Not the elements of that thing, is it? This is the symmetric group on these points. So the things we're permuting we'll just label as 1 to n, as is common. So G is a permutation of these n points. And then, so the point is, given any permutation of n points in here, you get an automorphism defined by sending a different, any permutation, and you send it to, F is our automorphism name. You send it to the conjugate by G. And so, like, why is this an automorphism? Just, well, I guess it's clear enough that it's a homomorphism, because, well, let's just do it. Let's do it properly. So, what's f of? It's got two things, x, y. That's going to be, by definition, G x, y, G inverse, and then you can do the trick of sticking a G inverse G in the middle, like so, and then this is f of x, this is f of y, and so there you go. That's your homomorphism. That's what the definition is. And so to check it's an automorphism of Sn, you've got to just check it's invertible. Well, that's easy enough, because the thing sending x to like conjugation, but the other way around is an inverse. So I'll call it f prime. Will turn out to be, let me do this in my notation, but I'll call it f prime. Will turn out to be the inverse. Define that to be g inverse x g. So it's the same as the definition of f, but we swapped where the inverse is on the g's, and then obviously, it's easy enough to check that that's an inverse of that. If you substitute this in for x here, then the two g's, the g and the g inverse cancel on the left and on the right, and you're left with x. So you've got an inverse for f. Therefore, f is invertible. It's an automorphism of Sn. And so these are called the inner automorphisms, the ones that you get in this way by conjugating by an element. So what we have is denoted like this in of Sn. And you kind of want to say it's going to be isomorphic to Sn, because for every element of Sn you get an inner automorphism. But you have to be careful, because it could be that two different elements of Sn give the same inner automorphism. And this is what sort of was mentioned earlier about S2. And this is what goes wrong for S2, is that this is possible. Because if you think about S2, it's very simple to think about. What is it? It's permutations of 2 points. So it's got two elements. We've got the identity element, which I'll call ID for identity. And then we've got the permutation that swaps the 2 points, 1 and 2. So 2 swap. See what I did there? So that's S2. So then, what are the inner automorphisms? Well, if you conjugate by the identity, you get the identity. So that gets sent to the identity automorphism. This one, what happens? If you conjugate the identity by this thing, let's do it. 1, 2 there. So you give an input, it swaps 1 and 2, does nothing, and swaps 1 and 2 again. So that's equal to the identity. So in other words, what we've shown there is conjugation by this guy fixes this guy, and similarly, if you conjugate this guy by itself, you sort of swap. You do this. You swap 1 and 2, then you swap 1 and 2 again. You swap 1 and 2 again. You end up with swapping 1 and 2. So this is also fixed by conjugation by this. So that gets mapped to the identity. So you see exactly this thing happens where two elements of S2 both map to the same inner automorphism. So actually, this is not true. When n is 2, you get the inner automorphism group of S2 is just the trivial group. Yes. So I guess what I said earlier. So S2 is not going to have any non-trivial automorphisms, and I guess you can see that as well, because automorphism group of S2 is the same as the automorphism group of C2, which we've just done already, which is the size of this is 1. So that's a nice link back to cyclic groups. But for S2 it goes wrong. For any other one, Sn with n bigger than or equal to 3, the inner automorphism group is the whole. All the things get sent to distinct automorphisms. Why? Because, the reason is because there's nothing in Sn when n's bigger than 3 that commutes with everything. If we look at our conjugation by G, we want to figure out, we want to show for any G that there exists an X such that x is not equal to gx, g inverse. And that's, if and only if gx does not equal, well, it doesn't really matter, xg is not equal to gx. So, this is equivalent to every element g. For every element g, there exists an element x that it does not commute with, and it's the set of things which commute with everything is called the center, which is denoted z. And so this is sort of equivalent to saying, if you know what this is already, if you're not, don't worry, that this is well, the size of this is 1, because obviously the trivial element always does it. Anyway, all that is to say, we have this for n bigger than or equal to 3. Cool. So that's your inner automorphisms. Are there any more, is the question. So you take it in Sn, you take the full automorphism group of Sn. We know we've got all the inner automorphisms, and they're quite nice and well behaved and understood in terms of things that commute or not. But are there any more? And this is like not obvious, definitely not obvious to me. I think it's not obvious at all what the answer is. For example, take S5. We know we've got 5 factorial 120 automorphisms from conjugation. Are there any more? Like, are there any isomorphisms from S5 to S5 that aren't given by conjugation? How do you sort of even begin to approach figuring this out? What do we think? How would you begin to approach ruling out that any of these things exist? Does anyone have any ideas on that? All right, well, I'll tell you then. I guess the reason you can start ruling these things out is because if you've got an automorphism, it's quite restrictive. To be an automorphism, you've got to preserve everything about the group. So, you've got to preserve the order of each element. We've already seen that in terms of you've got to fix the identity element. You've got to preserve the order of each element. You've got to preserve conjugacy classes. You've got to preserve all this stuff. So if we look at let's show that. Let me just scroll through my notes. Let's do it for S4. So let's show that the automorphism group of S4 is and is no bigger than the inner automorphism group of S4. So how are we going to do this? We're going to do it by looking at conjugacy classes in S4. Let me know in the chat or say something if you don't know what a conjugacy class is. But the short version is you have the relation of conjugacy in S4, as in for x and y, you say x is conjugate to y if there exists. So this is the same as if there exists a g such that x is conjugate to y, meaning you have this sort of thing. So so that's x is conjugate to y, and then this is an equivalence relation. So it partitions your group into conjugacy classes, and then automorphisms have to preserve conjugacy classes because they're defined in terms of the group structure, and automorphisms preserve the group structure. So let's look at what are the conjugacy classes in S4, and then that will give us some hints about what automorphisms can possibly be, and eventually let's rule them all out other than the inner ones. So S4, what are the conjugacy classes? Someone must know, so say it. In symmetric groups, there's a sort of nice characterization of conjugacy classes. Who knows what that is?
Is it like the cycle types?
That's right. Yes. So, yes, exactly. So in symmetric groups, the conjugacy classes are the same thing as the cycle shape of a permutation, which means if you have your permutation in disjoint cycle notation, whatever, maybe we got something like this in a group. The cycle shape of this is 2-3 cycle, I guess it's called, because you've got a bit that swaps 2 and a bit that swaps 3, and these are disjoint. And the conjugacy class that this thing belongs to is all the permutations of this cycle shape. So 4, 5, 1, 2, 3 will be in the conjugacy class, and so on. And now we have a 2 and a 3 cycle. Exactly, it's good stuff, isn't it? Best talk ever.
And so that
those
two, for example, are conjugated by whatever sends 1, like 1 to 4, 2 to 5, 3 to 1.
Exactly. Yes. So the G in this. Let's do it. So this is X. If that's X and that's Y, then the G that says that these two things are conjugate is the permutation that sends 1 to 4, 2 to 5, 3 to 1, 4 to 2, and 5 to 3. And I'll leave that as an exercise for why that's true. But I think it's hopefully sort of clear. If you conjugate this thing by this permutation, you apply the permutation. Well, maybe you start with these things. Where does 2 go? You do your G inverse, that takes you up here. Now you've got a 4. Then you apply your Y. I guess this is all backwards. Whatever. It's up to inverses of G. You go one way, you apply one of these things, and you come down again. And now you've just done that. And similarly for the other ones. So yeah. Exactly. So that's your G. Up to inverses, because I can't be bothered to figure out which way that should be. So that might be G, that might be G inverse. I don't know. You can check. And it doesn't really matter because it doesn't matter because there exists a G inverse. You can replace G with G inverse, and it doesn't change this definition. Anyway, so conjugacy classes in here are the same thing as cycle shape. So to figure out what the conjugacy classes are in here, you just have to figure out what are the cycle shapes. So let's do a table with the cycle shape and then how many things we have of each cycle shape. And if I'm feeling really mad, I might write them all out, but probably not. So we got cycle shape, and then we got how many permutations have that cycle shape. I'll do some examples as well, but probably not all of them because it's got 24 elements. So cycle shape 1, that is the identity element. Bit degenerate of the case. There we are. I've got ID to be consistent. Cycle shape 2, so that is 2 cycles or 2 swaps. Since we're in this particular Discord chat, how many 2 cycles are there in S4? Exercise. I'll start writing some out. I'll start writing some out over here. But yeah, someone tell me how many there are once you know. So we got 1, swapping 1 with 2, swapping 1 with 3.
I think 6.
Or choose 2. Yeah.
There we go. 2 people said the correct thing. 6. Yeah. So it's, you got exactly, you got your 4 elements that you could permute, and we want to choose 2 of them to be part of our transposition, our 2 cycle. How many ways of doing that are there? 4 choose 2. There's 6 ways. So I'll write them all out for this one. Since I've begun. What am I missing? 1, 2, 1, 3, 1, 4.
2, 3.
2, 3.
2, 4, 3, 4.
3, 4, and 2, 4. There we are. All right, that's cycle shape 2. Let's do the 3 cycles next. So that's things that look like this. So that's 1 goes to 2, 2 goes to 3, 3 goes to 1. Things of this shape. How many are there in S4?
8?
It is
Question
8.
mark?
Why is it 8?
So there's 4 items that you can leave out, and there's 2 like directions that the cycle can go in. So 4 times 2.
That's a nice way of saying it. Yep. So you got 4 choices for the thing you're going to ignore, and then you can either go that way around, or you can go that way around. So for each one, you got 2 more. So it's like I said, 4 times 2, 8 choices, 8 3 cycles. Right, 4 cycles. How many of those are there? Getting trickier.
I think it should be 6.
It is 6. Why is it 6?
So one's gonna have to go to something, and there are 3 choices of what to send it to, and then so we'll say 1 goes to, I don't know, 2 without loss of generality, and then there's just 2 options remaining.
Yeah. So 1 goes to 2 without loss of generality. That's right, how many choices have you used there? So you've used, I guess you haven't used, 1's got to go somewhere, so you pick 1 just
Yeah.
arbitrarily. You haven't chosen anything. There's
Right.
3 places that could go, and then
Yep.
that one's got 2 choices where it could go there,
basically.
and then
just
you have to finish it like that, or it could go there, and you have to finish it like that. Great.
And
There we are. So there's. Were you gonna say something?
No, I was just saying, like, yeah, just I guess in general it would be like n factorial, like cycle shape n things in a group of size, like a symmetric group of size n.
Sure. Yeah. Right, but
And -1 factorial.
Thank you. Yes.
thank you. Cycle shape 2 squared, meaning things that look like this. Oh God, that's not a number. Things that look like this. How many of these are there? It's the last one. You'll be pleased to know. I guess you can figure
But we
it out.
could just take
If you know
24
it's the
minus.
last one, you could just do exactly 24
Yeah.
minus that. So it is.
Wait, 24 minus 1? I was expecting it would be. No, just kidding. 3?
Well, 1 has to go with something. Yeah.
3. Yes. And there's only 3 of them, so we might as well write them all out briefly. So, what are they? They're the one that swaps that pair, and that pair. There's 3 of them. Right. What have we learned? We've learned that if we got an automorphism of S4, it's got to fix all of these. It hasn't got to fix them. It's got to permute the conjugacy classes in some way. The only 2 that have got the same order, the same size as these 2. So it's got to fix this one, and this one. It could swap these 2, but it can't, because things in this one have got order 2, things in this one have got order 4, and automorphisms also preserve things of order 2 and order 4. So all of these things are fixed by any automorphism.
Is that true in general and not just on symmetric groups?
Yeah, that's true in terms of automorphisms have to permute conjugacy classes
Oh, cool.
and preserve the order of elements. Yeah. Yes. But basically,
And-
because conjugation is defined in terms of the group structure, and automorphisms preserve that. Were you going to say something else?
I was just trying to think about why, like, if you have the inners, that will basically, like, I don't know, cycle everything with all of its conjugates. So you get all of those conjugacy classes. So an outer must go beyond that.
You could have an outer. Well, in principle, you could have an outer automorphism that fixes all the conjugacy classes. We're not quite there yet.
We would just have to do something weird with them that isn't covered by the inner.
Yes, exactly. Yeah.
Okay.
In principle, you could have that, but it turns out you can't because there's a thing. There's a thing that says theorem. If an automorphism, I'll type it. Let me use typing. Bigger. So, come on. If an of Sn fixes all 2 cycles, then it is inner. And that's not entirely obvious. But if we have this, once you know this, you then know that every automorphism of S4 has to be inner because we know every automorphism fixes the 2 cycles. When I say fixes 2 cycles, I mean fixes the conjugacy class of 2 cycles. If it fixed all 2 cycles, then it would be the identity automorphism because it's this group's generated by 2 cycles, and the same is true of all the other symmetric groups. So fixes there just means fixes as a conjugacy class as a whole, not necessarily all the points in it. So we can prove this. It's not too hard to prove. Do we care about proving it? It's slightly tedious. How bothered are we about proving this right now, or do we want to press on to get the outer automorphism of S6 quicker? Vote.
I
Quick vote.
would like to see it. I vote for yes.
Anyone else? Otherwise, we're doing it. All right, we're doing it. Fine. Let me get that up because I do not remember it off the top of my head. Might be a second. Oh god. As soon as you want to find something with people waiting, it all goes horribly wrong. Right. All right, let's do it. So, why is this the case? We need a. Well, okay. Let's rule out n equals 2. We want to assume n's bigger than or equal to 3. So n equals 2. Like we've done it for S2 already. We can just assume n's bigger than or equal to 3. Okay, because this is true of S2. Because this has trivial automorphism group. There's only the identity one. So every automorphism is inner because every automorphism is the identity one. Okay, so for n equals 2, it's trivial. We don't need to worry about n equals 2. N equals 1 again, even more trivial. So we're going to assume n is bigger than or equal to 3. Right. First thing to show. If you've got a pair of you take a product of two cycles, so x, y, z, w. There's 3 cases that can happen here. So if case 1, like the set xy is equal to the set zw, and that in that case, that happens if and only if the product Let's call this something. Should we call this something? I'll just write it out. If and only if x, y, z, w is the identity permutation. Hopefully that direction is clear. Going the other way will follow once we've done all the other cases if it's not already obvious. So that's case 1. Case 2, like one of these things are equal. So we'll just say x is equal to z. So like these have got one thing in common. We're going to assume these are two cycles, so x is not equal to y. So if this and this got one thing in common, then what happens when you take that product? Who knows this one? I guess we can do an example. If you got like 1, 2, 1, 3, what do you get? You get 1 goes to 3, 3 gets fixed, so 1 goes to 3, 3 goes to 1, and then 1 goes to 2. So 3 goes to 2, then put in 2, 2 gets fixed by this one, 2 goes to 1, so that's back to there. You get a 3 cycle. So these have got one in common, you get a 3 cycle in general. And if x, y, z, and w are all different, so all different, then, well, it's already disjoint cycle notation to begin with, so you get a 2 squared cycle. And these are all go both ways, these implications. So if you get a 3 cycle, the product of two things is a 3 cycle, then exactly one of these is equal to exactly one of these, and so on. So hopefully that's sort of obvious enough, and we're going to use that in a moment. Okay, so bear that in mind. Like, anyone unhappy with that, say something in chat or something. I'm going to move on. If not, so let's do the proof of the theorem. So we're going to let me do text because that is better than writing. Let call it f from Sn to Snb an automorphism fixing 2 cycles. And so we've got our automorphism, it fixes 2 cycles. What we want to show is that it's inner. So we want to end up with a permutation such that f is given by conjugation by that permutation. So how do we do it?
Can I ask a clarifying question?
You may, yes.
This means that every 2 cycle goes to a 2 cycle, not necessarily not necessarily that it fixes all of them.
That's right. Yeah. So when I say fixes 2 cycles, I mean sends every 2 cycle to another 2 cycle, but not necessarily the same one. If I was talking about sending fixing all the 2 cycles,
that would just be the identity.
F would have to be the identity. Yeah. So
okay.
Yeah. Exactly. Yeah. So fixing 2 cycles just means every 2 cycles goes to a 2 cycle, not necessarily the same 2 cycle you started with. Good to clarify. Okay, so what's the next step? We're going to look at where does f send some things. Where does f send this? Where does f send this? Where does f send this? And so on. Well, we know f. Well, we're going to look at where f sends the product of these things. So f of 1, 2, 1, 3. We know that is f of the 3 cycle 1, 3, 2. And automorphisms preserve 3 cycles. So that means that f of 1, 3, 2 is a 3 cycle. And by our thing up here, if you end up with a 3 cycle, it means 2 of your 2 cycles you started with, they both show exactly one thing. So that means f.
Why
of,
do we know that automorphisms preserve 3 cycles?
That is a good question, because any 2-3 cycles are conjugate, and automorphisms preserve the relation of being conjugate. Are either of those two not clear?
But could you, like, just theoretically, we could send all 3 cycles to all 3 squared cycles?
I see what your objection is. Give me a second.
Like, I understand. I can take this, like, for granted. It's just not immediately obvious.
Okay, that's a good point. That is a good point. I think the fix to that is you don't. This is not necessarily a 3 cycle, but it definitely has order 3.
Yeah.
Right. That fixes it. Yeah. Yeah. No, fair enough. Good point. Valid objection. So this might not be a 3 cycle, and but it definitely has order 3. And we know that the f of okay, so we know f of 1, 2 is some 2 cycle. Now this we know, this doesn't encounter your objection because we're assuming f fixes 2 cycles. So this we do know. This is equal to some other 2 cycles for the same reason. We know that the product of these two has order 3 because you're applying f to something of order 3. And so by this thing, the only way you can have order 3 as a product is if 2 of these things are equal. Okay, so
Okay.
Exactly one of these two is equal to exactly one of these two, and the other two are different. All right. So that is to say, there's some A, and there's some A, B2, and B3, such that f of 1, 2 is A, B2, and f of 1, 3 is A, B3, right? Because we know these two things have to share at least one, exactly one thing in common. And I guess this also shows B2 is not equal to B3. Otherwise, they'd have 2 things in common, and the product would have order not 3, which we know it does. All right. Are we all still following? Are we all happy?
And A is also not equal to B2 or B3.
That's right. Yeah,
nitpick.
because this is yeah. So yes, we've got that as well. We got that as well. Correct. Okay. And then you basically just do the same thing for all the other. You keep going. So this, by the same reasoning, must be A, B4 for some B4 not equal to anything else, and so on. F of 1, anything is A, B, something that's different to all the other ones. So we've got this. So we've now got A, B2, B3, all the way up to Bn, all distinct. And if you recall, what our goal was, we're trying to show that F is an inner automorphism. So we're trying to find an automorphism by which F acts by conjugation. So we've got some distinct things. Let's define a permutation like this. So we're going to define G will be defined to be the thing sending 1 to A, 2 to B2, 3 to B3, and so on. And now all that's left to check is that F acts by conjugation by G. And so how to do that? Yeah, on each 2 cycle of this form, we'll check it. So F of this, we already know, is the two-cycle ABK. And this is the conjugate of 1k, and I'm going to get my inverses modelled up, so someone correct me if I get this the wrong way around, because I'm not checking or thinking about it in the slightest, but it's going to be this, possibly with the inverse on the other side. Shall we just actually check? So G inverse will send A to 1. So this is the wrong way around, isn't it? I think. So we need the inverse on this side. So G now will send 1 to A. No, I had it right the first time. Never mind. G inverse will send A to 1. 1 then gets mapped to K, and then K gets mapped back to B, BK. So this sends A to BK, and similarly sends BK to A. So these two are equal. And so F acts by conjugation on two cycles of this form. Sn is generated by two cycles of this form, and so therefore f of anything is equal to G x G inverse. So therefore f is inner as an automorphism. Are we happy? Are we happy?
Yeah.
Great.
Cool.
So we've shown now, done everything to show S4. We've shown this. We've shown the whole automorphism group of S4 is just the inner automorphisms. Great. Not quite at S6 yet. We can do S5, and that's basically the exact same. So what's the automorphism group of S5? And so we now know all we need to show is we need to count things of cycle shape whose elements have order 2, and then show that like they've all got the wrong size for 2 cycles to get mapped to them. So it'll be more clear once I write it out. So we do the same thing as we did before. Cycle shape and how many things. We're not gonna do all of them because you don't need to. So what do we need? We need, how many 2 cycles are there? Answers, shout them out.
20.
That's not what I've got. I don't think it's 20.
10. Wait.
Yes.
Yeah, 10.
Why is it not 20?
I think I double counted the symmetric pairs, like the flipped equivalent. Like I just naively did like 5 times 4, but like you have to divide by 2 because
yes,
the ordering matter or doesn't matter.
Right. Yeah. Right. Sure. You had me worried for a moment there. You said it was like confidence. Yes, exactly. So this is 5 choose 2, 10, because you got 1 for every pair. Great. Let's do. So we're just going to do all the ones that have all the cycle shapes that have order 2. That's all we need. And the only other one is 2, 2. E.g. because I know this notation is not necessarily standard everywhere. These sorts of things, 2 cycles. So how many of these are there in S5? I guess this one's slightly trickier.
15?
15?
That's right. Why is it 15?
I was just multiplying it by 3 and then dividing by, but like, because for the second pair, it's like there's 3 options, but then you double count by twice, so you have to divide by 2.
Yes. Cool.
Yeah.
Yep. Cool. Yep. So great. Great. So it's not hard to see, if you think about it for a sec, that these are all the possible cycle shapes in S5 whose elements have order 2. So if you have an automorphism of S5, it has to either swap these two send everything in here to something in here and send everything in here to something in here to have a bijection between these two, but these are not equal, so there is no bijection between the two. So because of our theorem that any automorphism preserving these things is inner, every automorphism of S5 is inner. So we got this one as well.
Oh, I don't mean to. I think I see how this is going to culminate with S6 having.
You can spoil it if you want. Go on.
Well, I haven't done that. I haven't actually worked it out yet, but I mean, it looks like the way this is trending is something's going to equal the other thing here.
Sure, yeah. Let's do that. Let's do it. S6. And then yes, we get into the really nice stuff with S6 and constructing the outer automorphism. Spoilers. Right, so S6, what have we got? Oh, you don't want that. 2 cycles. How many?
15.
15. Yeah. That being 6, choose 2, same as all the other ones. Disjoint pairs of 2 cycles. How many of those are there? And then the other one, of course, is 3 disjoint 2 cycles. So we've got these 2. What are these 2?
105?
105 is not correct.
So it'd be 75?
45?
Is it 45?
45?
It is 45. Why is it 45?
So I guess I'll give mine. So there's going to be two things that are not in a cycle or of order 2, and then that leaves 4 things remaining. So there's 15 possible pairs of things that don't get mapped anywhere. And then among the remaining 4, there's 3 possible pairings between them. So 15 times 3.
Great. So yeah, there we go. You got these choices. 45. Cool.
Oh,
you happy?
that's the same because you can swap the 2 you left out.
Yes.
Huh. That's cute.
Have I missed? Have we? Did we just figure this one out and I've missed it?
Yeah, well, I think Greg Huber just said it, right?
Wait.
What was the reasoning?
There's duplicate.
Wasn't it supposed to be 45?
Because there's 3 ways, like given one of these 2, 3, they correspond to 3 of the 2 squared, depending on which of the 3 you leave out.
Yeah, so if you just sort of call this another transposition, you've counted it ordered, as in you got these 2, and then this one's separately special. So you have to divide by 3 to account for the fact that this one could be there, there.
Right. Yep.
So that you got to divide by 3 there. And get your
I thought for a second it was 45, but then I was like, that doesn't make
you
sense,
said that. Yeah, I thought the same
the
thing.
2
Yeah.
wouldn't, the 2 cycle, the whole proof breaks.
Yeah. Yeah, so then we wouldn't have any outer automorphism, then we'd have broken maths.
Yeah.
So the C2 that shows up is precisely the C2 of swapping the cycle shape 2 with the cycle shape 2 cubed.
That's correct. Yes.
Cool.
Yes. I'll just make that explicit. So yeah, I said earlier, the automorphism group of S6 is going to be same around C2 times S6. These ones being the inner ones, and then this being the outer ones. And the fact, this is C2 because you're swapping these 2. So your outer automorphism sends these to these, and then you do it again. You send them back to 2 cycles, and therefore you're back to being inner again. So you've got to be back to trivial here. Exactly. Okay, so but this doesn't show that there is an outer automorphism. It just, at this point, we can't rule it out because there could be something. There could be an automorphism sending 2 cycles to 3 disjoint 2 cycles. But we don't know that that's the case yet. We haven't you know, it's just sort of a big clue that that might be something that could happen, and obviously it is, because I wouldn't be talking about this if it wasn't. So okay, something could exist that does this. Why? What is it? What's going on? That is what we're going to do next. So let's do that. So how are you gonna construct something that does this? A sort of weird automorphism of S6. I'll outline the idea. So the idea is you think about 6 points, which I will draw now, and I'm going to draw them in a sort of funny pentagon-y shape for no particular reason, just makes the diagrams that are going to happen a bit nicer. So we think about our 6 points like this, and we're going to define some stuff. So I'll do these because we're going to need them. First thing we're going to define is a duad, which is just silly name in the case of 6 points for, you're never going to believe this is thrilling stuff, an edge between two vertices. That's called a duad. Because it sounds more cool that way, basically. That's a duad, easy. Syntheme is the next one, another silly name. What is that? That is 3 disjoint ones of those. So 3 edges, no 2 of them going to the same node, same vertex. And finally, and most excitingly, pentad. Pent because it's going to be 5 disjoint synthemes. So let's do an example of that. So let's put one, well, let's do the same one we've got there. To start with, why are we not blue? Come on, blue. Why is it not blue? Come mad. Thank you. So, right, pentad, for example, you could have that one. We could have, where can we go there? There's a 2. Let's put a yellow one in. Where can we go? Is it going to work? Can't go there. We can go there. And we can go, we can't go there. We can go there and there. That works. We can go there, there, and there. And there should be exactly one more we can squeeze in there, there, and what am I missing? These 2 there. So that is an example of a pentad. We've got 5 disjoint synthemes between the things. Okay, what's the point of all this? The point is we're going to show, or it turns out that there are, so how many of these are there? I guess, well, first of all, it's worth noting how many of these are there. Well, it's the same as the number of 2 cycles. It's like literally the same, same thing. So the number of these is 15. Like these are basically the same thing as 3 cycles. So there's 45 of those. Any guesses how many pentads there are?
Those are the synthemes are the 2 cubed cycles, right?
Yes.
Which there are 15 of?
Yes, you're right. I've had a brain fart. Correct. Thank you. Thank you very much. 15 of those. Yeah. Yeah, these are not 2 squared cycles. These are 2 cubed cycles. Yes, 59 is right. These correspond to these guys. Thank you. Right, how many pentads are there? So it's worth pointing out the order doesn't matter here. It's just a partition of the edges into 5 disjoint synthemes. The order doesn't matter. You know, you could swap the red and the yellow colors, and it's the same pentad. So it's not obvious at all what the answer is here, but you could have a good guess. Just chuck a number out. Any guesses?
3?
3? Any others?
I kind of want to think about this.
You can. I'll give you 10 seconds. Actually, well, we can leave it. We can come back to this. And maybe at some point you'll go, it must be whatever it is.
No, I know what it is.
Or do you want to say?
I think it is 3.
You think it's 3? Ooh.
I think it's 3. Shall I? Wait. No, just kidding. No, I don't think it's 3.
Just kidding. Just testing. We'll leave it for now as an open thing, and we'll definitely come back to that. So, okay. Let's prove some stuff about these 3 things. Fact 1. I'll type this one. Every duad is in 3 synthemes. So, okay. Why? It's fairly easy enough to see why. You start with 6 points. You say, here's my duad. How can this possibly be completed to a syntheme? And there's going to be 3 ways of doing it. So you could go. You could do. You can go there. You can go there. And you can go there. Right, there we are. So, and that's all of them. You got your 3 possibilities. So these are the only 3 synthemes containing that duad, and it's all of them. Cool. So hopefully that's clear. Right, a nice thing to know. Fact 2. Any 2 disjoint synthemes look like this up to permutation of points. And so what is this? This is going to be basically, because it's any 2 synthemes look like this, is the thing we're trying to show. It's just pick any 2 that are disjoint and they will look like this. So for example, this, any 2 will look like this. So why? So what do I mean by up to permutation of the points? Like if you sort of drag the points around and drag the edges with them, you start with any 2 disjoint synthemes, you can end up with this after some permutation of the points. I mean, just sort of think about it for a minute and it's clear enough. Like slightly less hand wavy than that. I mean, you can obviously get the 3 blues. If you ignore the reds, you can get the 3 blues there, and there by permutation of the points. Now,
you have to, like, you could pick one of the 6 points.
Yeah.
And then it has to go to one of the other duads. It can't go to the same. And then the other side of that duad has to go to the 3rd.
Yes.
Otherwise, that third would be duplicated.
Yes, yeah. So if we ignore the reds for a second, this you got the let's say put the blues where they are. This one has to go. Like we've got this one. This one has to be connected to something by the other syntheme because every syntheme touches every vertex. That's got to go there. Then you've got another blue, and then this one can't connect back to the duad you started with because if this was red, let's make a green one. If you got a green there and a green there, then this would force the last green one to go here, but you're blocked by this blue one. So you have to, the red one has to sort of go from the first blue duad to the second one, and then the second one to the third one, and then back. So you have to have a sort of loop like this that goes through all of them. I can see the people typing 24. We'll come back to it. Well, I'll tell you you're wrong, so you can keep thinking. We'll come back to it. So yeah, so you have to have a loop that sort of goes through if you connect up all the bits, and therefore, like swapping within the blue ones, you can put the reds, yeah, exactly here. So we have this. Hopefully that's clear. Dang it, yeah. You'll go, oh, of course, when you get it. Right, what's next? What are we on? Fact 3. What is fact 3? Any two disjoint disjoints in something belong to a unique pentad. Why? Let me copy over from here. So you start with any disjoint pair of synthemes where we know it looks like this. Well, yeah, let's start with the one we just shown actually is equal to. So we know any two disjoint synthemes look like that. And then it's, yeah, you basically have to just show that there's a unique way of completing this, and sort of everything's forced. So it's basically what I was doing at the start when I was filling in this diagram that we do next. Everything's forced. So you say some syntheme has to go here, whatever it is, we'll call it yellow, and then everything else is forced. So yellow, you can't go yellow here. You can go, so this is one possible completion of yellow. Is there any more? Well, the only other options are actually no, something's gone wrong, isn't it? Because we can do that, or we can do that, which shouldn't be possible according to what I just said.
Maybe one of them breaks further along.
That's true, yes. It must do. Yeah, what happens? So if we go there, way.
It seems like
it would just.
one.
Have I got this wrong? Let me double check this. Does it go wrong? Let's try it. Let's try both. See what happens. So if we go here, so if we complete it there, that's one possibility, and that's another. Does something go wrong in one of these? So okay, something's got to go here. That's not allowed. That's not allowed. So we have to go. Oh, that's not allowed. Yeah, so in this case, I guess nothing's allowed. So green, your possibilities for green are here, blocked by the blue. Here, you're blocked by the yellow. And which one have I not done? Here, blocked by blue, blocked by yellow. And there, you're blocked by the red. Right, so this one's not possible. So yellow has to be like this, and then green, everything at this point is definitely forced. Well, let's just check it. So whatever edge goes here, green you got 3 options for the green. You could go there, it's blocked by the blue. You got like this, but it's blocked by the red, so you have to go there for the green. And then now it's just fill in the remaining stuff. So you have to have there, and there. Okay, right, good. Didn't all collapse. So cool. Right, so we got this. What is next? Aha, right. 2 swap, last chance. We're up to the, it's not 12. We're on to the fact, which is how many there are. So final guesses in, we're about to spoil it.
Wait, sorry. Did I miss? Like, was there a proof for the previous fact, or did we just?
This one,
Yeah.
fact 3. There was, yes. We started with this,
Yeah.
and you just add stuff until everything's forced. So you just add stuff. I'll do it again very briefly.
Well,
So
I experienced everything being forced, but I'm not convinced that was a proof.
okay, so well, any 2 disjoint synthemes look like this by this fact.
Yeah.
And then when we filled it in, we said, well, in a pentad, whatever syntheme is here, we'll call it yellow. And then we can try and complete yellow like this, but we ran into a problem, so it can't possibly be like this. It can't go here because we've got the blue edge. So yellow has to go here, and similarly, everything else was forced, and you have to end up with this.
Is that necessarily going to be like representative of all possible like initial choices for how we started, or?
Yes, because any two ways of starting, you can permute the points and make it look like this by fact 2. So however you start, you can just rearrange the points so it looks like this.
I guess so. Yeah.
Yeah.
Yeah. Okay. Yeah. I believe you.
Good. Cool. Okay, so we've got fact 3, fact 4. Right. About to spoil how many pentads. Did I make up the word syntheme? It is a cool word. I did not make it up. It just seems to be the word that is used in the context of the outer automorphism of S6 for whatever reason. And it is a cool word, so I'm using it. Right, fact 4. Any last guesses on the number of pentads? Going once. Going twice. All right.
Don't tell me it's like the monstrous moonshine number.
No, it's not. There are 6. There are 6. And it's no coincidence that we started with 6 points. We got 6 pentads, and we're doing stuff with S6. But we'll get to that. So why are there 6? Well, it's a sort of choices argument again. So we'll start with our 6 points. So, okay, we're trying to make a pentad. Whatever it is, it's going to have a syntheme that connects those 2. So we'll just call that syntheme the blue one. At this point, there are 3 choices for what blue could be. Right, you could go here, you could go here, or you could go here. So there's three choices. Let's make one of them and sort of tot up that we got 3 choices that we've picked between. We've ended up with this. And now, I think we had a fact. I guess that's using fact 1, but maybe we didn't have a fact. Okay. That is fine. The point is there's going to be 2 ways of extending this to a pentad. So why are there 2 ways? Well, okay, right, fine. Yeah, so whatever syntheme connects these 2, we'll call it red. And now there's 2 ways red could be. You can't have red here because it's blocked by the blue. So you can either go there or you can go there. So we've got 2 choices for that. And now by fact 3, these 2 complete to a unique pentad. So there we are. So we made 3 choices. for the blues, 2 choices for the reds. So there's 6 possible pentads. Was that clear enough?
Yep.
Good. Okay. So now we can do some stuff. So let me copy in a picture, if I can figure out how, of a picture of all 6, with some extra bits. There we are. So there are all 6, and there's they're sort of connected here in this picture by faint sort of edges, making it into a sort of graph, a complete graph on 6 vertices, where the vertices are pentads, and it's not directly relevant, but these sort of these faint edges connecting the pentads. That's in blue, and that means this pentad and this pentad share the blue syntheme, and they share no others. So I guess this sort of structure isn't. I don't think we proved this just yet, but I guess at this point, don't worry about the background edges. The point here is just that there's 6 pentads. Here they all are, and now we get our construction of the outer automorphism. So the outer automorphism, how do you do it? So we need to call our 6 points. I'll call it. So call the permutations of the 6 points. I'll call it sim k6. So that's sort of being complete graph on 6 points. Let's draw that here. So that's k6. K, because we're adding edges, but really it's just the 6 points. So this is the permutations of the 6 points. And now if you permute the 6 points, you're going to induce a permutation of the 6 pentads, right? You know, if you sort of pull this this over here and swap these 2, you're going to get a different pentad. And so basically you end up with a group homomorphism here from permutations of this to permutations of the pentad. So I'm going to let K6 prime denote the 6 pentads. So this is, let me draw it as a horribly drawn pentagon, and then we have whatever are 6 of these. So that's K6 prime. And so, right, all that is to say, you permute these, that induces a permutation on these because you're shuffling the vertices around. And so you get a homomorphism here. And the thing is that is an isomorphism. More than isomorphism, it is an outer automorphism. If you match these points up in any way you like, which is sort of equivalent to picking an inner automorphism, then you end up with this is sort of the same as an isomorphism of S6 that's outer. And so we've constructed it, except I haven't shown that it's outer and I haven't shown that this is an isomorphism. But that sort of gives you where it comes from, hopefully. Have I lost anyone there?
Wait, one thing I'm curious about is, so when you say in the kind of the faded pentad, like when something's colored red, that means it shares only the red edge?
Yes.
Like, is it guaranteed that like 2 of these will never share 2 or more, or is it kind of constructed that way?
It's
every pair shares exactly 1 syntheme.
That's right. Yes, I don't think we've shown that yet, but it is true.
The picture shows it, whether or not
okay.
you do.
Oh.
Yeah.
So like,
and also,
no, carry on. Oh, like the edge at the very bottom that's red.
Yeah.
That doesn't mean the bottom edge is red. It just means that like all the red edges are the same.
Yeah, it means the
It
red
mean-
syn themes are the same between the two that it connects.
It means that
Okay, I
this
see it now.
this pentad and this pentad share the red syn theme.
And
they
no
have
others.
that in common, and no others in common.
Yeah.
And
Yeah, I'm kind of noticing a pattern. Yeah. It's kind of like symmetrical for all the outer ones.
Yeah, it's all very nice,
Yeah.
like symmetrical.
It's crazy that
And
works
and,
that way.
and you sort of look at what pairs things have. You look at all the yellow ones in the background, and that makes a syn theme of pentads.
Yeah.
Yeah,
And you get this funny recursive like
that is cool.
going back. And like this is kind of related to the fact, like we've sort of reasoned before, if you do an outer automorphism twice, you get back to an inner automorphism. If you take the pentads of pentads, so based on this graph, you end up with something in canonical bijection with the points you started with. So this pentad of pentads in the background corresponds to that point. And other pentads of pentads correspond to other points, but canonically, not any choices. Can I give an example of an evaluation of this automorphism? Yes, we can go on. We can look at how things act. So, yes, let me do that. And yeah, let's try and show that it, well, I guess there's two things to show. We want to know, why is it an isomorphism? Because at the moment, we only know it's a homomorphism. Yeah, you might not end up with all possible permutations of the pentads. You might just end up with a subset by permuting the points. So we want to show it's an isomorphism, and we want to show that it sends 2 cycles to 3 disjoint 2 cycles, so that it's an outer automorphism. So which one do we want to do first? Doesn't matter really. But yeah, okay.
Do we know that this is a homomorphism?
Yes, but I guess it's not immediately obvious. Like, okay, so why is it a homomorphism? Because if you swap, what do we want to show? You want to show if you do a permutation here, followed by another permutation here, and then look at what happens. That's the same as doing a permutation here and looking what happens. A different one, like the other one, seeing what happens and then composing them here.
Yeah.
Like,
Is just because we're linking each point with one of the pentads?
yeah, it's because the two things are linked, like,
Okay.
by this combinatorial construction. That
I guess I don't understand how it's clear that it's a homomorphism but not an isomorphism, since they both seem like they act like S6.
Well, it's a homomorphism because of what we just said, because these things are defined in terms of the points, and so like permutations here are like compatible with ones here. You don't know it's an isomorphism because, well, why how do you know, for example, that there's some permutation of the points that let me get a color. How do you know that there's some permutation of the points that does this, that sends that one there, that one there, that one there, and that one there, and fixes those two? I mean, it's not obvious that some permutation of these points would do that. At least it's not obvious to me. If it's obvious to you, and you can see a good reason why, then I'd love
Could you
to
explain more than what like the map between them is?
What do you mean by the map between them?
Like the sim k6 to sim k prime?
Yeah, so sim k6 is a permutation of the 6 points.
Yeah.
And sim k6 prime is a permutation of the 6 pentads. So we will have a function which takes a permutation of the points and gives you a permutation of the pentads. And like what that is just if you swap these 2 points, how does that sort of drag the edges on the pentads? And therefore, if you start with
Oh,
we
okay.
can do an example if you want, but if you start with this pentad and then you drag that edge to that one and that one to that one, you're going to end up with a different pentad, whatever it is.
Okay. That helped me get unlost. Thank you.
Great. Anyone else lost? Anything else confusing? All right, I'll assume we're okay. So, yeah. So why is it an isomorphism? Why do you get all permutations? One way of doing it is just by hand check all the permutations, like check all the permutations of the 6 points on a computer or whatever, and just find that you get all of them. I guess that's the computer scientist's version. I don't know a maths version, sort of a handwritten by hand version, that doesn't assume that you know the following fact. So the fact that the normal subgroups of S6 are the trivial one, A6 and S6. Has anyone seen this, not seen this? I can't prove it now because it's meh. If no one is happy with that, then there's not a lot of point. Well, maybe there's a bit of point showing how you can use this, but if we're happy with it, I can do that. What do we think? Are we happy with this?
I'll run with it.
You can believe it. Yeah. Yeah, I guess I'll leave that. I have to leave it unproved. I mean, I do know the proof I have it, but it's far
I'm
too
guessing
much
what
version.
I've seen for A5 would probably mirrored to A6.
You know it for A5, do you?
Something to do with the 3 cycles.
Yeah, that's right. There's a proof.
So is this the same proof?
I think the way you do it typically is you do it for A5. So you say the equivalent of this for A5, and then you do an induction to show it for all. So this is true for all SN. Bigger than 5, bigger than or equal to 5. This is true.
Cool.
Yeah. Okay, we'll assume this. And if you want to know why, yeah, Google it another time. So how do we use this to show that this is an isomorphism? The idea is you show that, well, this is sort of an action, right? So this is a group action of another way of saying it, it's a group action of this group on this set. This is equivalent to a group action of permutations of these points on the set of pentads. And the fact we need is that action is transitive, meaning, so transitive is kind of a weaker version of what we want. What we want is that every possible permutation is achievable of the pentads. Get anything we want from the permutation of the points. Transitive just means if you pick one and say I want it to go there or wherever, there's some permutation of the points that does that. So maybe for this one, I don't know what it would be, whatever it is that achieves it, there's something which sends this wherever you want. So transitive is you can send any pentad, pick a pentad, you can send it wherever you want, but there's no guarantees about what these ones do. So why do we have transitivity? Let me remind myself why we have that. Well, let's assume that for now, since we're in this zone. So let's assume for now this is transitive, and I'll show in a second. If this is transitive, then you sort of ask, what is the kernel of this homomorphism? So let's give things names. Let's say this is called F again. So F from sim K6 to sim K6 prime. So we're going to ask, what's the kernel of F? Meaning, so if you don't know what kernel is all the permutations in here that induce no permutation here. So maybe you swap these 2 points and nothing gets permuted here. So it's all the permutations here that end up doing nothing here. And this is an isomorphism if and only if the kernel is trivial, i.e. like every permutation does something here. Because that'll give you, it's equivalent to being injective. And these two have got the same size. So you're injective if and only if you're bijective. So anyway, so we want to figure out what the kernel of F is. If the action is transitive, which is what I'm claiming but not proven yet, that implies that the kernel implies something about the size of the kernel. So if you're transitive, what is it? It's not quite the kernel, is it? It's let me get this straight, otherwise I'm going to make everyone confused. What am I trying to say? Let me get it up so I don't get this wrong. Bear with. That's helpful.
Is it like at most 120?
Yes, exactly. It's you're trying to bound the size of it. So let me write what it is I know we want. So we're trying to show the index of the kernel in. We're trying to show the index of that in that is at least 6. So, right, help me out. Why is that the case if the action's transitive? Why does that imply that the index is at least 6? The index is the size of the quotient group.
6 distinct elements to get mapped to.
That's right, perfect, thank you. Yeah, so there we go. So the index, wow, this isn't. So the index is the size of the quotient group. Because you're quoted by the kernel, you get an action of this quotient group on K6. And we know the action of the quotient group is transitive. So the quotient group, where's this? There's got to be something which sends this to where it is now. It's got to be something which sends it there, 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 something which sends it there. So you've got at least 6 elements in the quotient group because, the action of the quotient group by the kernel of the action is the same as the action of the whole group. You get the same stuff. So this has got to be at least 6. On the other hand, we know the kernel of F is a normal subgroup. Is normal in your sim 6, and we know from this fact, which I've not proven, there's only 3 possibilities. This one, A6, has index 2. So if you quotient by A6 here, you're only going to get 2. It's too small. If you quotient by S6, you're going to get 1, which is too small. So the kernel has to be trivial. So therefore, the kernel of F is trivial, and therefore F is an isomorphism. Right, thank you for bearing with me there. Does that make sense now that I remembered why it's the case?
Yeah.
Great. Okay, so we got an isomorphism now. We know it's an isomorphism.
And we know it's transitive because if we could pick any two and then come up with something that goes between them.
Yes, that's true. We haven't shown it's transitive. So what you reckon? Go on. Why do we know it's transitive? So let's say I want to send that one here. How do we know there's some permutation of the points which does it? I don't think it's obvious at this point. I think we need one more fact. Yeah, okay, we'll do one more fact, which will make it clear. So, what fact are we on now? Go 4. Looking for numbering them, call it 5. So, this one's also gets at one of the questions I saw. Can we actually look at what a bit more explicitly this action does? So, fact 5 is if you have a synth theme, call it that. And let's get our pentad K6 graph beautifully drawn. So if you have a synth theme and you apply that we've got that 2 cubed cycle, then the thing that happens over here is a 2 cycle. So this is actually going to show that it's transitive eventually, and it will imply that we've got an outer automorphism, because it will imply that the conjugacy class of 2-3 cycles is swapped with the conjugacy class of 2 cycles. So it'll actually do everything we wanted. So the claim is if you do the 3 cycle of a synth theme, you get a 2 cycle on pentads, and more specifically, I think we've shown earlier. Did we show? We showed. Maybe we didn't. Okay, well, we'll show as well now that any synth theme belongs to exactly 2 pentads. Well, I guess this is what we were talking about earlier in the graph. You know, any synth theme, there's exactly 2 pentads it belongs to.
Well,
we did that.
Is that true? We did do that, did we?
I don't think we did, but there's 6 and each has 5, and there's.
Oh, there was this point we kind of reasoned it here with the times 2. Right, because we started with our as part of this one we got our blue synth theme, and then we sort of figured out there's 2 ways of completing that to get your pentad.
Yeah.
So yeah, we do have this. We do know this. We did it earlier. Rewatch if you've forgotten. So yes, we do know this blue synth theme is contained in exactly 2 pentads, and the claim is that if you apply the 3 cycle of the synth theme, you will get the 2 cycle here that swaps the 2 pentads it contains and fixes the other 4. Yes, how do we show this nicely? I guess at this point there's a slightly easier computer science proof where you just do it on one of them, and because everything's sort of symmetric, it's fine. That's a bit yucky. How can we show that nicely? I know how to do this bit. It's how do you show that it? Let's do that bit to start with. Let's show that it swaps the 2 that contain it, and then worry about why these things are fixed later. So it swaps the two that contain it. Well, because what are the two that contain it? There's two ways it could go. So whatever syntheme's here, we'll call it red. And so red could be that, or it could be that, basically. Those are the only possibilities. And if you swap all of the blue, if you sort of apply this blue 2 cube cycle, I think you'll find that these two get swapped. Is that right? No, it isn't, is it?
Doesn't seem like it.
No. What do you get? You'll get that. Well, let's just do it. So let's see where does red go here? Red, that one will go there. That red will come here, and that red, that red will go here. So you'll end up with that. Maybe I don't want that one to be red over here. I want it to be whatever it is. Oh no, I do. I don't know. No, I do. I think. So this is we know this will give the other pentad, however it gets completed. Let's see where red goes. There, and there. I guess then you can sort of just complete these however they are, however they have to be. Not like that. Not like that. Oh dear. Where's it got to go? Are we buggered? Can't go there, can't go there. Can't go there. Can't go anywhere. Oh, because, okay, that's because this orange one isn't, right, so, okay, so I guess this is one way of seeing it. If you apply the 2-3 cycle of blue to the red one, you get the orange one. And this red and this orange can't belong to the same pentad. In other words, if you complete the red one and the blue one, you get one thing. If you complete the orange one and the blue one, you get another one. They can't be the same because there is no pentad containing all three of them. Because of this, if you try and complete all three of them, you run into this issue here with yellow. You got an error there. You crash with blue, and there you crash with orange. There you crash with blue. So I think that shows, although perhaps not particularly clearly, that if you swap, if you do the blue 2 cube cycle, you'll send the two. It won't fix the two that it sends that contain the blue syntheme, and obviously the two you get will contain the blue syntheme, and they're not fixed, so it's got to swap them. Does that make sense? Because I was stumbling through that a little bit, or I can go through it again, maybe clearer.
It makes sense why they're swapped. It's still unclear why the other ones are not.
Great, yeah, fair enough. I haven't done that bit yet. Yes, okay, so we're happy that this happens. Why are these all fixed? Okay, that's what's left. Good question. Yes. Yes, very good question indeed. Let me see. Let me see if I've got it. Oh, it gets so horrible. it's easier to go the other way. As in, okay, right, fine. Well, we don't know these are fixed, but this does at least show. Does this show the action's transitive? Is that enough now, at least? I think so, because let's say
Does any two share?
any two share a syn theme, and you just apply that two cube cycle.
Yeah. Okay.
So-
Sorry for leading
Yeah.
down that path that's unnecessary.
No,
That
that's what I was
the
going.
others are all fixed.
No, that's what I thought we were going to do, but I think it's easier to do it the other way. So the other way being, what does a two cycle do to pentads, and show that a two cycle here gives you a two cube cycle on pentads, and then because you've got an outer automorphism of S6 and it swaps two cycles with two cube cycles with two cycles, then you'll get this implication here, because you've got a two cube cycle and you know that that's going to go to a two cycle. And you know that these two are swapped, so these two then these will have to be fixed. But that's only once you know you've got an outer automorphism, which we don't yet. Does that make sense?
Yeah.
Yeah. So if we can show that two cycles give you two cube cycles over here, then you've got an outer automorphism, and then that implies that. Okay. But for now, this does at least show that we're a transitive action, so it implies that we are an automorphism, not necessarily outer yet, because we don't know that these things are fixed. Right, let's do the final fact, and I think I'll call it a day there, which will show that we're an outer automorphism. So this one's the same as this one. It's going to be, well, not quite the same. If we start with 6 points, I'll copy the pentad diagram. If we start with 6 points here, and we have the two cycle of a duad, the claim is that that's going to give us a three cycle here. Not three cycle, a two cube cycle. All right. Okay. I've lost the proof of that one. Oh, literally had it up a second ago. There it is. Okay. Can we do it? So okay, we're going to look at how does, rather than looking at how it acts on pentads, we're going to look at how this thing acts on syn themes. So there's two cases. The first one is, well, we're going to take a syn theme. So the first case is that your syn theme contains the duad, so something like this. And the second case will be that it does not contain the duad. So something else, for example, that. Right, so this one contains our duad, this one does not. I'm going to look at how does this act on this. So I guess this is easy enough to see. What's going to happen? So where's this? What syn theme does this get sent to? So if you apply this two cycle to the vertices of this, what syn theme do you end up with here? Is anyone still awake? Test.
Itself?
Yes. Exactly, yeah. Yeah, because we just swapped those two, so that's just, the edge remains there. Great. Let's do a little, that's if you apply the blue. What about this one? What's that going to get sent to? I guess it's harder to describe, so I think hopefully it's clear that it's going to get sent to
The Roman
this.
number 11.
Thank you. Yes, very good. Great. So okay. So what does this? So we know how this acts on on synthemes. How does that translate to pentads? So let me figure this one out in my own head, and then I can explain it better. Okay, so if you have a pentad, exactly one of its synthemes. Let me get a pentad. Let me grab one so we can point at something. So we have a pentad. Let's go over here. So you have a pentad. Oh, luckily the blue is blue. That's nice. So exactly one of the synthemes in here contains the duad. And by this, that syntheme will be fixed when you apply this this duad. And the other four are changed. They're not only changed, they're changed to something that cannot possibly be in the same pentad, right? Because this edge is fixed by applying the 2 cycle. So these two synthemes cannot belong to the same pentad. So what that means is if you apply this 2 cycle to this, you get something different, basically, different. Right? And this is true for every pentad. There's nothing special about that one. So applying this to any pentad, you get a different one. That must imply that you get the 2-3 cycle here because nothing's fixed and it's order 2. Huzzah. Are we happy with that?
Yeah.
Great. There we are. We've got an outer automorphism of S6. Thank you very much. I'm going to end it there. I'll take questions though.
Very nice.
Irony.
I'm guessing that like for above 6, it's a way to show that the number of 2 cycles doesn't match anything else with order 2. I don't want to
what was that?
dive down another rabbit hole.
I think I missed
like to show that there's no outer or higher than 6.
Oh,
yeah, I was wondering the same thing.
The
like
2 swaps.
Yes, that's true. Yes, we've done. What have we done? Oh, we've done S1's trivial, S2 we did, S3 we did, S4 we did, S5 we did. We've now done S6. So we did these ones by conjugacy classes. We didn't do S3, but that's you can do that on homework. Those two we did. And that one was just done. So yeah, what happens for Sn n bigger than or equal to 7? Like I claimed that. It's the inner automorphism group at the start. It's not anything, and it is. I'm not going to prove it now, and the proof's a bit horrible, but I can give the idea of the proof because it's quite nice. So the idea is, I'll do my last fact, and I won't prove it, but I'll outline the proof idea. Fact 7. For n bigger than or equal to 7, the number of 2 to the k cycles in Sn is strictly bigger than number of 2 cycles in Sn, and then hopefully by the stuff we did earlier, that implies all
Okay.
automorphisms are in it, and that's for all.
So it is a conjugacy class based argument.
Yes, exactly. Yeah.
But that's not to say that 2 to the... Well, what if like 2 to the k is like what if 2 to the 2 cycles equals the amount of 2 to the 3 cycles?
That's fine because our fact from before. Let's go. Where's it gone? Have we gone too far? Gone too far? That one.
That one.
If it fixes all 2 cycles, it's inner. So we just have to show that the class of
gotcha.
2 cycles doesn't go to any other class.
Right.
So yeah, doesn't matter if the higher ones are equal or not. That's enough. Yes. So the proof of this is a bit just calculation-y. I'll give the idea because it's quite nice. So let's go. We've got n and k here. K equal to 2, 3, 4, 5, and so on, and n is equal to. We'll start at. I've done this. Hang on. I prepared this. Or did I? Maybe I didn't. Oh, I did. Good. N equal to 4, 5, 6, 7, 8. I have to go quite far. Let's go, and so on. So these circles represent the fact that that this is true. Was it? No, it is this. This fact 7. If it's true for n and k, if the number of 2 to the k cycles is bigger than the number of 2 cycles in Sn, we're gonna tick the circle. It'll be clear what's going on in a second. And so what's going on is in S4 you've got 2 squared cycles and that's it. In S5 you've got 2 squared cycles and no more. In S6 you've got 2 squared and 2 cubed. In S7 you've got squared and cubed. In 8 you've then got 4th power ones and 5th power and so on. And so the circles we need to tick off sort of go on in this pattern. You sort of step up by 1 every 2 you go along. Okay, so we're going to tick them off if this fact 7 is true for that particular n and k. 4 and 5, I guess we'll tick it off if they're not equal. These are just, well, they kind of tick it in orange because it's not quite the same. Not part of, this is for n bigger than 7, but still kind of nice to have them there. S6 is not true because, well, I guess for it's not true for this one. For this one, it's true, but that's enough to say you could have an outer automorphism, which you do. So it's all the big ones that are interesting and the stuff that we're asking about. Why is there nothing here? Why is that there? So, okay, how's the proof go? The idea is you check it the same way as we've already done, just sort of list out the conjugacy classes for 7 compared to 2 square cycles, compared to 2 cube cycles, and for 8 compared to 2 to the 4 cycles. So you do these ones manually, and then you do an inductive step that sort of shows if you've got one. You do 2 inductive steps. You go, if you've got one here, you get one here. So a tick there implies a tick there, and you do another one that says if you've got a tick here, and then sort of in the grid there, then you get a tick here. So these are 2 inductive arguments you do, which is sort of counting arguments, horrible and tedious, but you can do it. And then this sort of implies that one ticks that one, that one ticks that one, that one ticks that one, and so on. That one ticks that one, and so on. That one ticks all those. This one by this one ticks that one, and that one does all those. That one ticks that one, and so on. That's sort of the structure of the inductive argument that you have to do, and then you get your fact 7. And therefore, all your automorphisms are inner for Sn with n bigger than or equal to 7. I'm not going to go into the details of the inductive steps, but if anyone does want to see that, I can probably put them in a document and post it at some point for the details.
Cool. This outline feels satisfyingly enough. I can take this at face
Yeah.
value. Thanks for.
Yeah,
Yeah,
so I
they
just-
sound like kind of nasty calculations.
Yeah, maybe I can just. I've got it in my thing. Maybe I'll bring it up just to show you the what it actually looks like. I mean, yeah, it's got lemmas apart. Right, let me I'm gonna have to tell Discord to change the screen it's showing. Bear with, let me just get this open. Yeah, okay, let me stream the other screen. 1 second. Okay, so that's what I just drew. So we've got this, so the number of elements, you sort of count the number of elements of cycle shape 2 to the k as something, and you have a big nasty inductive argument. Well, it's not too bad, it's just that it's a bit messy to show that, and then you do it. Yeah, we're trying to show that this is not equal to the thing which is counted above. That's the number of 2 cycles, that's the number of 2 to the k cycles. And then, like, there's some argument that you do of just a bunch of algebra to check. Cases less than 5 we've done explicitly, bigger than 7. You want to show that. Well, you show this inductively. There's your 3 base cases. I said that one, this one, this one, this one, which you just check explicitly. Then there's your inductive steps, and then you sort of check them. So it's not horrific, but it's a bit messy to all write it out. So there.
I'm slightly confused about why the 4 column is colored green.
Because
aren't there fewer?
So the thing I've stated here is the number of.
Oh, it's different.
I've stated it just as different, yeah, for n not 6.
Okay.
Yeah, basically the same thing. But yeah, for these ones you just show it's bigger. For these ones it's different, but that's fine. So yeah, there we are. Any final stuff, or I'll be going to bed where I am.
I'll cut the recording.
Great, thank you.